Section 10.2, Hypothesis Testing for Population Means where sigma is known. In Section 10.1, we covered all of the fundamentals of hypothesis testing, but we really didn't get a chance to put it all together, which is what we're going to do in this video. So in the last section, we looked at stating the null and alternative hypothesis, which is the first step. Determine which distribution to use for the test statistic and check conditions. We haven't talked about that yet, but we will in this video. 3. Identify the sample statistics. 4. Use Excel to calculate the test statistic, critical value for the rejection region, and the p-value. And then 5. Draw a conclusion and interpret the decision. So in this video, we're going to hypothesis test for population means where sigma is known. We're going to use the exact same conditions. The population standard deviation is known, the sample size is taken from a simple random sample, and either the sample size is at least 30 or the population distribution is approximately normal. Then we will find the test statistic, which is a z-score. And that z-score is found by taking x bar minus mu, which remember that's observed minus expected, and then divided by the standard error. So not the standard deviation, but now the standard error, which for sigma known means is sigma divided by the square root of n. Recall we said we would look at two different ways. We've already talked about finding the confidence interval, but now we're going to talk about finding the critical value for the rejection region and finding the p-value. So first, we'll take a look at how to find the critical value for the rejection region. The rejection region is determined by two things. First, the type of hypothesis test. So whether it's a left-tailed test, right-tailed test, or two-tailed test, and that all depends on the alternative hypothesis. When the alternative hypothesis is less than, that is a left-tailed test. If it is greater than, it's a right-tailed test, and if it's not equal to, it's a two-tailed test. In addition, we must know the level of significance, or the alpha level. How do we make a decision based on rejection regions? Well, it depends on where our test statistic falls. If our test statistic, denoted Z, is to the left of our negative critical value for a left-tailed test, we will reject the null hypothesis. If Z is to the right of the positive critical value for a right-tailed test, then we will reject the null. And if Z is either to the left of the negative value or the right of the positive value for a two-tailed test, then we will reject the null. Now that might be difficult to visualize, so let's take a look at a great visual to help us understand what's happening. If we are running a left-tailed test, then we're going to have a critical value that is to the left of our mean. So that's why it's denoted negative Z sub alpha. Notice that the entire value of alpha is located in the left tail. If our test statistic falls within that tail, then we'll reject the null, otherwise we'll fail to reject. For a right-tailed test, we can see that all of alpha is in the right tail. So Z alpha, which we can find by norm S inverse 1 minus alpha. If our test statistic falls within that rejection region or to the right of our positive critical value, then we will reject the null, otherwise we'll fail to reject. And if we're running a two-tailed test, keep in mind that alpha is split between the two tails. So note that when we're finding those critical values in Excel, we're going to use alpha divided by 2. So the negative critical value of alpha divided by 2 is norm S inverse of alpha divided by 2, and the positive is norm S inverse of 1 minus alpha divided by 2. Again, if our test statistic either falls to the left of the negative or to the right of the positive critical value, then we will reject the null, otherwise we fail to reject. Let's take a look at how to set up our spreadsheet to run a hypothesis test for means where sigma is known. Note that I've left a space for my null and alternative hypotheses. They're both mu. The null is always mu is equal to, and then some input. The alternative is going to be mu is either less than or greater than or not equal to the same input that I have for my null. You can either just go ahead and enter the alternative hypothesis yourself, or if you are a dork like I am and like to have the drop down where you can choose from the list, all you have to do is choose a column like I did, leave the first one blank so that it starts as blank, and then put less than, greater than, and not equal to, which is found in the insert symbol. Then you will choose the space. You will go to Data. Under Data Tools, there is a Data Validation, and you will choose the source. You'll choose List and Source F1 through F4, which is where I have my data. And then in Cell dropdown and click OK, and then you'll have a little dropdown like me. If you don't want to do that, that's just fine. The sample mean, X bar, will be an input, standard deviation, sigma, sample size, alpha level, all of those will be inputs. The standard error is the population standard deviation divided by the square root of n. The test statistic is a z-score, and it's just standardized, but keep in mind the first value is the observed value, which is the sample mean, and then the expected value, which is our null hypothesis, and then D9 is our standard error. So we're not using standard deviation, but standard error. Then we're going to use the critical values that we just went through on our last slide. For a left-tailed critical value, norm S inverse of the alpha level. For a right-tailed, norm S inverse of 1 minus the alpha level. For two-tailed, the easiest way to do this is to find the positive critical value. Remember, this is the two-tailed test, so there's a negative and a positive. So if I do norm S inverse of 1 minus alpha divided by 2, I get the right-tailed critical value. So for a left tail test, we're saying if our test statistic is less than our critical value, that means it's in the rejection region, we reject, otherwise we fail to reject. For right-tailed, if D10 is greater than D13, so if the test statistic is greater than the critical value, we reject or fail to reject if not. And then for the two-tailed, just make sure you use the absolute value, since this is always going to give us the positive critical value, and this will make the test statistic positive so that we can compare it correctly. Example 1. The State Education Department is considering introducing new initiatives to boost the reading levels of fourth graders. The mean reading level of a fourth grader in the state over the last 5 years was a Lexile Reader Measure of 850L. A Lexile Reader Measure is a measure of the complexity of the language that a reader is able to comprehend. The developers of a new program claim that their techniques will raise the mean rating level of fourth graders. To assess the impact of their initiative, the developers were given permission to implement their ideas in the classrooms. At the end of the pilot study, a random sample of 1,000 fourth graders had a mean reading level of 856 Lexile. It is assumed that the population standard deviation is 98 Lexile. Using a 0.05 level of significance, should the findings of the study convince the Education Department of the validity of the developer's claim? Step 1 is to state the null and alternative hypotheses. We are expecting a Lexile Reader Measure of 850L. So the null hypothesis is that mu is equal to 850, or the mean Lexile Reader Measure is 850L. The alternative hypothesis has to do with the developers who feel that their intervention will raise the mean Lexile Reader Measure. So mu is greater than 850. The mean Lexile Reader Measure is more than 850L. Step 2, determine which distribution to use for the test statistic and check the conditions. This one's pretty easy because the only test that we know how to run is a hypothesis test for population means where sigma is known. But again, we are given information about the population mean where the population standard deviation is known, so we're going to use a z test statistic in the normal model. The conditions is the simple random sample, which is met, sigma is known, which is met, and n is equal to 1,000, which is certainly greater than or equal to 30. Next, we are to identify the sample statistics. In this case, the observed value, or x bar, is 856. The population standard deviation is 98. N, or the sample size, is equal to 1,000. And alpha is 0.05 because we are given that it's a 0.05 level of significance. Let's now enter our data into Excel. So again, our null hypothesis is the 850 that is expected. Notice that it's 850 in both places. Our alternative hypothesis, we said that it was going to be greater than, which means that when I'm looking at my data here, I'm only going to be looking at that right-tailed critical value and result. The sample mean was 856, standard deviation 98, N is 1,000, alpha level 0.05. Everything else gets done for me. And again, because this is a right-tailed, I'm going to the right, I'm saying greater than, this is the value that I'm looking for. So 1.9361, my test statistic, is greater than 1.6449. So my decision is to reject the null hypothesis. Now let's draw our conclusion and interpret the decision. The test statistic of 1.9361 falls in the rejection region, so we reject the null hypothesis. That's our conclusion. Let's interpret what that means. There's evidence to suggest that the education department can be 95% sure that the mean Lexile reader measure of fourth graders will increase. And again, increase ties back to the alternative hypothesis, which was that mu was greater than 850. So we've just determined how to construct a rejection region using the critical value. But another way to draw a conclusion, and in fact the most common way found in research articles, is the p-value. The p-value is always compared to the alpha level to draw conclusions. Recall that a p-value is the probability of obtaining our sample statistic, or one more extreme than our sample statistic, based on the fact that the null hypothesis is true. So if that p-value is very large, then the probability of obtaining that statistic is very large. We're not surprised that we found that statistic because that's a high probability. But if that p-value is very low, and again, how low is too low? We're going to use our level of significance. If p is less than alpha, that means the probability of finding this result is very low, and there's significant evidence to suggest that the alternative hypothesis is true. So if p is less than alpha, we reject the null in favor of the alternative. Again, what we're saying is the probability that, assuming that the null was true, that we found our results is so low that we're surprised by the results and we say, it must be that the null hypothesis was false. On the other hand, if p is greater than alpha, the probability that we found our result, assuming that the null was true, is very high. Again, we're not surprised by that because the probability is so high. Therefore, there's not sufficient evidence to say that the alternative is true, so we fail to reject the null hypothesis. So if p is greater than alpha, we fail to reject the null hypothesis. So we're going to go to that very same spreadsheet that we've already started for 10.2, and we're just going to add 3 more rows. So again, left-tailed p-value, right-tailed p-value, two-tailed p-value. Now keep in mind that whatever happens for a left-tailed critical value, if we reject or fail to reject, should also happen for the p-value. Same for right-tailed, these results should agree, and two-tailed results should agree. So again, how do we do this? The left-tailed p-value is going to be based on going to the left of the test statistic. So norm S dist D10, 1. That's to the left of the test statistic. To the right is 1 minus norm S dist, D10 minus 1, or I'm sorry, D10 comma 1. And then again, we're going to use the positive value. We're going to take 1 minus norm S dist, absolute value of D10 comma 1, and we're going to multiply it by 2 since it's two-tailed. Again, what are we looking for? We're looking for if my p-value is less than D8. So if the p-value is less than alpha, we reject, otherwise we fail to reject. Same here. If p-value is less than alpha, reject, otherwise fail to reject. Same for two-tailed. So all we're going to do is add those 3 rows. Going back to the example we already completed using the critical value, we noted that we would reject the null, that the education department can be sure that the mean Lexile reader measure of fourth graders will increase based on that alternative hypothesis of greater than. We can use the same thing with the p-value. The p-value is 0.0264, which is less than the alpha level of 0.05. Therefore, we reject the null. So note that these results agree. Example 2, you can go ahead and try this one on your own, and then we'll go through it together. A researcher claims that the mean age of women in California at the time of a first marriage is less than 26.5 years old. Surveying a simple random sample of 213 newlywed women in California, the researcher found the mean age of 27 years. Assuming that the population standard deviation is 2.3 years and using a 90% level of confidence, determine if there is sufficient evidence to support the researcher's claim. Again, don't let yourself be overwhelmed by this. Just take this one step at a time. First, what's the null and alternative hypothesis? Well, first of all, we're dealing with means, so we know it's going to be mu, and the null is always equal to, and it's always equal to what we would expect, or the status quo. So again, the researcher claims the mean age is less than 26.5. So we're assuming that it is 26.5. Not that it's less than, but it is exactly 26.5. So that's the null. Mu is equal to 26.5. The mean age of California women when they marry is 26.5 years old. The alternative is based on the researcher's claim that California women at the time of first marriage is less than 26.5 years. So the alternative hypothesis is mu is less than 26.5. Now again, we already know which test to use. We're given information about a population mean where the population standard deviation is known. So we're going to use the Z test statistic in the normal model. The conditions are SRS, which is met, sigma is known, which is met, and n is 213, which is greater than or equal to 30. Next, let's identify the sample statistics. We know that the observed mean, or x bar, is 27. The population standard deviation is known to be 2.3 years. N is 213 for 213 newlywed women, and alpha is 0.10, which is 1 minus 0.9. Let's go ahead and use Excel using those values. So our null hypothesis was that it was equal to 26.5, and the alternative hypothesis was that it was less than 26.5, which means we're going to be looking at the left-tailed critical value and the left-tailed p-value. The sample mean is 27, sample standard deviation 2.3, sample size 213, and alpha 0.01. And we can see based on the left-tailed value, the critical value is negative 1.2816, and the test statistic is obviously not less than that, so we fail to reject. The p-value is very high, which is 0.9992, much greater than the alpha level of 0.1, and again, therefore, we fail to reject. Finally, we draw our conclusion and interpret the decision. With p approximately 0.9992, which is greater than alpha, and our test statistic not falling in the rejection region, we fail to reject the null hypothesis. That is the conclusion. We must also interpret what that means in context. There is insufficient evidence to suggest that the age at the time of first marriage is less than 26.5 years. For your final example, I'd like you to try this question on your own. A recent study showed that the mean number of children for women in Europe is 1.5. A global watch group claims that German women have a mean fertility rate that is different from the mean for all of Europe. To test its claim, the women surveyed a simple random sample of 128 German women and found they had a mean fertility rate of 1.4 children. The population standard deviation is assumed to be 0.8. Is there sufficient evidence to support the claim made by the Global Watch Group at the 90% level of confidence? Step 1, state the null and alternative hypotheses. Again, the null hypothesis will just be that German women average 1.5 children, just like the other European counterparts. The alternative is that they do not average 1.5 children, so mu is not equal to 1.5. Step 2, we already know which test to use, but again, we would test that this is a population mean where sigma is known. So we're using a z-test normal model. The conditions are simple random sample, which was met, sigma is known, which is met, and n is 128, which is greater than 30, so it's met. Step 3, identify the sample statistics. X bar is 1.4, that was the fertility rate for German women. The population standard deviation, or sigma, is 0.8. N is 128, and alpha is 1 minus 0.9, which is 0.1. Step 4, we're going to plug what we know into Excel. So my null hypothesis was that mu was equal to 1.5, an alternative not equal to. That tells me I'm using my two-tailed critical value and two-tailed p-value. My sample mean 1.4, standard deviation 0.8, sample size 128, and alpha level 0.1. So again, we have a test statistic of negative 1.4142. We would compare that to negative 1.6449, and obviously this value is not less than that, so that's a fail to reject. For the p-value, we are looking at 0.1573, which is certainly not less than 0.1. So again, that's a fail to reject. So let's draw our conclusion. We can see that p, which is 0.1573, is greater than 0.1, which is alpha, and the value of negative 1.4142 does not fall below negative 1.6449. So we fail to reject the null hypothesis. At a 90% level of confidence, the evidence does not support the watch group's claim that the fertility rate of German women is different from the mean for all of Europe.